Now, before we talk about sets, let's quickly do a recap on rational and irrational numbers. So what are rational numbers? Rational numbers are numbers that can be put in the form of fraction. They are numbers that can be put in the form of a divided by b, such that the value of b is not equal to 0. So examples of rational numbers, we have 2, 3 over 4, 5 over 8, 7 over 8. These are all rational numbers because they can be put in the form of a over b such that the value of b is not equal to 0. Now, what are irrational numbers? Irrational numbers are basically the opposite of rational numbers. They are numbers that cannot be put in the form of fraction. Now, examples of irrational numbers are, we have 3.316624, and then we also have 4.123105. Yes, so these are examples of irrational numbers. Now, these are irrational numbers because they have non-repeating decimals. Now, let's look at a value like 0.2 recurring or 0.2222. Is this a rational number or an irrational number? Clearly, this is a rational number because it has a terminating decimal. Now, this value 0.2222 or 0.2 recurring is equal to 2 over 9. And because we can represent this decimal value in the form of a fraction, it makes it a rational number. Now, let's move ahead and talk about the topic itself. So, what is a SURD? Now, a SURD is the square root value that cannot be written as a whole number or a rational number. So basically, that is the definition of a SURD. A SURD is a square root value that cannot be written as a whole number or a rational number. Now, to better understand this, let's look at the square root values of some numbers. So let's say we have the square root of 1, we have square root of 2, square root of 3, square root of 4, and then square root of 9. Now, square root of 1 is 1, square root of 2 is 1.4142, square root of 3 is 1.7320, square root of 4 is 2, and then square root of 9 is 3. Now, which of these values cannot be written as a whole number or as a rational number? Clearly, the square root of 2 and the square root of 3 cannot be written as a whole number or as a rational number. Therefore, square root of 2 and then square root of 3 are called SURDs. Now, some other examples of SURDs include, we have square root of 5, square root of 7, square root of 11, and so on. Now, let's talk about another important thing that is going to help us to understand this topic. That is perfect square. Now, a perfect square is basically a number that when you find the square root of that number, you are going to get a whole number. So 1 is the perfect square because the square root of 1 will give you a whole number, which is 1. Now, 4 is also a perfect square because the square root of 4 gives the value 2, which is a whole number. And then 9 is also a perfect square because the square root of 9 gives a whole number, that is 3. So some examples of perfect squares: we have 1, 4, 9, 16, 25, and so on. So now that we know about sets, we know the definition of a set, let's look at how we can simplify a set. Now under this, we are going to talk about two types of sets. We have a set that is already in the simplified form, and then we have another one which is not in the simplified form. Now examples of sets in the simplified form, we have square root of 2, square root of 3, square root of 5, square root of 7, and so on. These types of sets are in their simplified form, meaning that you cannot further break down these sets. So these sets are in their simplified form. Now let's look at some examples of sets that are not in their simplified form. So examples are the square root of 20, the square root of 100, the square root of 75, and so on. These types of sets are not in their simplified form. Now, if n is a number such that the square root of n is equal to or can be expressed as the product of a perfect square and another integer, then the square root of n is a reducible set and can be reduced to its simplest form. So what you are saying is that if you have a value, let's say n, so you have the square root of n, and you can express the square root of n as the product of a perfect square. Okay, let's assume a to be a perfect square and then another integer. So here we have b to be any other integer and then a is a perfect square. Then the square root of n is a reducible set and can be reduced to its simplest form. So basically that is what you are saying. Now let's solve an example on that. Let's say we have the set the square root of 12. Now what are the factors of 12? So factors of 12, we have 1 and 12, we have 2 and 6, and then we have 3 and 4. So now let's take 1 and 12 out. Okay, we are not going to consider 1 and 12. So 1 and 12 is out. So let's consider 2 and 6, and then 3 and 4. Each of these pair contains a perfect square. Now 6 is not a perfect square because the square root of 6 will give you a decimal value. However, the square root of 4 will give you a whole number, which is 2. So we are going to select 3 and then 4. We are going to select this pair. So we can express the square root of 12 as the square root of 3 times 4. Now let's split this expression. So we can have the square root of 3 multiplied by the square root of 4. So we have the square root of 3 multiplied by, now the square root of 4 is 2. So we have 2. Now root 3 times 2 is equal to 2 root 3. So the square root of 12 can be simplified as 2 root 3. Now let's solve some more examples. So for the second example, let's simplify the square root of 20. So the factors of 20 are, we have 1 and 20, we have 2 and 10, we have 4 and 5. Now because we are not going to select 1 and 20, let's focus on 2 and 10 and then 4 and 5. Now 2 is not a perfect square. However, 4 is a perfect square. So we are going to select 4 and 5. So the square root of 20 is equal to the square root of 4 times 5. So we are going to split that. So we have the square root of 4 multiplied by the square root of 5. Now square root of 4 is 2. So we have 2 times square root of 5. And then we have our final answer to be 2 root 5. let's solve the third one. How can we simplify the square root of 150? So 150 can be expressed as 6 times 25. So we can have the square root of 6 multiplied by the square root of 25. Now the square root of 6 is already in its simplified form, so we maintain that. However, the square root of 25 is equal to 5. So our final answer is 5 root 6. So the square root of 150 is equal to 5 root 6. So next, we are going to discuss how to add and subtract sets. So in algebra, you can add two like terms to form a single term, so that if you have a plus 3a, then this is equal to 4a. If you have 2b plus 4b, then that is equal to 6b. So because they have like terms, we just add their coefficients. So that's what we are going to apply in the addition and subtraction of sets. So for the first one, we have 2 root 3 plus 3 root 3. Now root 3 is common to both terms, so we just add their coefficients. So the coefficient of the first term is 2, the coefficient of the second term is 3. So we have 2 plus 3, which is 5, and then multiplied by root 3. So 2 root 3 plus 3 root 3 is equal to 5 root 3. For the second one, we have 4 root 2 plus 6 root 2 minus 7 root 2. Because root 2 is common to all the three terms, we have 4 plus 6, which is 10, and then 10 minus 7, which is 3. So we have 3 root 2. So for the third one, we have 13 root 5 plus 7 root 5 minus 2 root 5. Now 13 plus 7 is 20, and then 20 minus 2 is 18. So we have 18 root 5. And then for the last one, we have 5 root 11 minus 7 root 11 plus 13 root 11. So 5 minus 7 is negative 2, and then we add 13, so we have 11 root 11. So now let's solve some more complex examples. So for the first question, we have the square root of 72 minus 4 root 8 plus the square root of 200. Now to solve this, we are going to break down the sets so that we can add them. So the square root of 72 can be expressed as 2 times, that is the square root of 2 times 36. And then we have minus 4, and then the square root of 8 can also be expressed as 2 times 4. Then we have plus 2 times 100. Now what we are going to do next is we are going to split them. So we have the square root of 2 times the square root of 36 minus, we have 4 into bracket, we have square root of 2 times square root of 4, and then plus we have square root of 2 times square root of 100. Okay, we can also put this in a bracket. Now the square root of 36 is 6, so we have 6 root 2, and then minus, we have 4 into bracket. Now the square root of 4 is 2, so this reduces to 2 root 2 plus the square root of 100 is 10, so we have 10 by root 2. So let's simplify further. So we have 6 root 2 minus, now we can multiply 4 and 2. So we have 4 times 2 is 8. So that is 8 root 2 plus 10 root 2. Now because we have like terms, we can add and subtract. So we have 6 minus 8, which is negative 2, and then negative 2 plus 10 is equal to 8. So we have our final answer to be 8 root 2. Very simple. Now let's solve the second one. So for question 2, we have square root of 28 minus square root of 63 plus square root of 175. So let's solve together. Like we did in the first example, the square root of 28 can be written as the square root of 4 times 7. We have minus, and then 63 can also be expressed as 7 times 9. And then we have 175 as 7 times 25. So now let's split them. We have the square root of 4 times the square root of 7 minus we have the square root of 7 times the square root of 9, and then we also have the square root of 7 times the square root of 25. Now the square root of 4 is 2, so we have 2 root 7 minus the square root of 9 is 3, so we have 3 root 7, and then plus the square root of 25 is 5, so we have 5 root 7. Now because we have like terms, we can add and subtract. So we have 2 minus 3, which is -1, and then -1 plus 5 is 4, so we have 4 root 7. So this is our final answer, 4 root 7. So that's it for today's video.